Okay, in previous segments, we learned about probability distribution of one variable. All right, what if we are interested in two variables? And we need also to know what's the likelihood of occurrence of these two variables when they are observed together. Bivariate distributions will explain such phenomena. So bivariate distribution will tell us about the probability of the combination of these two variables that we are interested in. Okay, so what we did before is this. We had a variable x that can take different values. Let's say it can take the value 2 and 5. All right, and then we have a probability for each one of these values. Let's say it's 0.3 and 0.7. All right, we may also be interested to observe another variable y that can take the values 3 and 8, for example. Okay, and also we have probability of occurrence for each value of these. Okay, for example, 0.4 and 0.6. All right, we may need to observe these two together. For example, the value of x, which is 2, can occur when y is 3, and also x is 2 and y is 8. And also here we have x5, y is 3, and x5 and y is 8. So we may need to compute the probability of these combinations. So what the probability that x is 2 and y is 3, x is 2 and y is 8. This is what we mean by bivariate distribution. After all, it's exactly the same as any other probability, and you will see that the requirement for the bivariate distribution, probability distribution, is exactly the same as the requirements for any probability. Okay, so we have these two properties that we have seen many times now, that the probability should be between 0 and 1, of course, and the sum of all possible combinations, the probabilities of all possible combinations should sum up to 1, right? So, for example, here, when we find the probability of each one of these four combinations, certainly the sum of these probabilities will be equal to 1. So we start directly with an example that will illustrate the use of bivariate probability distribution and what we can tell from that, what we can derive from a probability distribution table. All right, so here we're given that two agents, Xavier and Yvette, they sell houses, and we collected data about the number of houses sold by each one of them. And then we combined them in one table, and we found also the probabilities of the combination of x and y, which looks like this. So how can we interpret this bivariate probability distribution? Okay, let's take any value here. For example, 0.21. What does it mean? This is the probability that Xavier sold nothing. All right, you see here the 0, and Yvette sold one house. And let's look at another one. For example, this one. What's 0.02? Okay, that's 2% probability. There is 2% chance that Yvette has sold 2 while Xavier has sold 1. All right, so this is how we read a bivariate probability distribution. Okay, so you see, when I started explaining this topic, I started by showing you that if we have two variable x and we have the probability distribution of x and y, then I can derive their bivariate probability distribution. Then what if now I don't have these original probability distribution of separately for x and y, but instead I have the bivariate probability distribution, so the joint probability distribution. Can I find from these the probability distribution of x and then the probability distribution of y? Yes, we can do that. Okay. Remember, we've done that before when we discussed the example of the mutual funds, whether they outperform or not the market. So here we go. To find the probability distribution of y, what we do, we find the marginal probability, and the same for x. So for y, we find the sum of the rows. Okay, let me first get my highlighter so that I show you. Okay, so see, here we have summed up the rows, and the first row summed to 0.6, and this corresponds to y equals 0. So 0.6 is the probability that y can take the value of 0. And for 1 it's 0.3, and for 2 it's 0.1. Now to find the probability of x, or the probability distribution of x, what we do, we sum up the columns. So also we are finding marginal probabilities, right? So this is p of x equals 0. We have summed up the 3, okay, and we find it to be equal to 0.4. P of x equal 1 is 0.5, and p of x equal to is 0.1. So these marginal probabilities give us the separate probability distribution of x and y. All right. As I told you before, we can derive a lot of information given the bivariate probability distribution of x and y. So we can find the mean, the variance, and the deviation of these variables. So let's see how to do that. We learned in the previous slide how to find the probability distribution of x and y from the marginal probabilities. So this is done, and we are showing them here. Here we go. So we have now these probability distribution. How to find the mean? Remember, we learned how to do that. Remember this equation. Mu is equal to the sum of x times px. So we multiply each value of x by its corresponding probability, and then we sum them all. Okay, so for x, can you find mu? Okay, I strongly advise you to stop the video now and do it on your own and check your answer. All right, so let's do it. Xp of x, okay, we multiply 0 times 0.4 plus 1 times 0.5 plus 2 times 0.1, and here we go. The 0 does not count, so I'm not showing it here. So it's equal to these two, and the value is 0.7. Mu y, we do the same, and we get 0.5. Now, what about the variance? The variance is given using this formula, and as I told you earlier, that it's always, whenever you want to use this formula, make sure that you do this element first and then deduct the square of the average. So for x, the variance of x, it's 0 squared times 0.4 does not count, so it's 1 squared times 0.5 plus 2 squared times 0.1, and then we sum these up and we subtract 0.7 squared. So this is what I'm doing here, right? So this part, okay, sorry, this part, it represents the first part here, okay? And then we subtract the square of the average and we get 0.41. And we do the same for y. Okay, again, I'm showing separately the first part so that I don't forget to subtract my average. And then we subtract this and we get 0.45. And the standard deviation is the easiest part because you know that standard deviation is simply the square root of the variance. So standard deviation of x, square root of 0.41. So we get 0.64, and standard deviation of y, we get 0.67.